an ODE with a delta function in it, right? We have our differential equation, initial conditions, and the right-hand side is a forcing term, which is just a delta function. What this means is that we have like our spring mass system, and at time 4 pi, we're hitting it, right? We're just giving it an instantaneous jolt of energy or force at time 4 pi. So what we should see, right, from this initial condition, if it's spring mass, we already have some oscillating going on. But at time 4 pi, something else should kick in our solution. Something else should be turning on at that time. So let's go ahead and solve it. We have s squared capital Y minus sy of 0 minus y prime of 0 plus 5 capital Y. And the Laplace transform of this delta function is e to the minus 4 pi s. We have y prime of 0 is 0, and we have y of 0 is 1/2. So this becomes capital Y times s squared plus 5 equals e to the minus 4 pi s, and then this term looks like plus 1/2 s. So continuing, let's continue here. Capital Y is e to the minus 4 pi s times 1 over s squared plus 5 plus 1/2 s over s squared plus 5. We're basically ready to invert. In this particular problem, we don't have a partial fraction that we have to do. We don't have a completing the square that we have to do. We're ready to just do the inverse, which is nice. That can happen with the delta function because the transform of the delta function is just the exponential. With step functions, you have other stuff in there, and it often turns into partial fractions or completing the square. But not the case here. In this particular problem, we don't have to deal with that. We do need a square root of 5 up here for this to look like the table. So let's do one more rewrite and say that capital Y is e to the minus 4 pi s times 1 over the square root of 5 times the square root of 5 over s squared plus 5 plus 1/2 s over s squared plus 5. We now have these two terms, and each is ready to read off the table. They're both table-ready terms. And so our solution is y of t equals, when we do the inverse now, the exponential is going to become a step function, t minus 4 pi. So we have our step function, and then we have, oh, I made a mistake here. This parenthesis goes around this term, but not the other term. So I don't actually need a bracket here at all. There's only one term that was multiplied by the exponential in the Laplace transform. So only one term when I invert is going to have to deal with that. And so I have 1 over the square root of 5 times, this is the sine, and it's the sine of the square root of 5 times t. Now remember, when I've had the exponential multiplied by the Laplace transform, I don't just put t, I put t minus 4 pi. So it's not sine of root 5t like it would be. Instead, it's sine of root 5, and then t is replaced by t minus 4 pi. The other term doesn't have an exponential on it. The other term is free of that exponential now that I fixed the parenthesis. And so that is just a 1/2. This is an s, not a 5. So that's an s, and that inverts to a cosine. So that is the cosine of the square root of 5 times t. So you can see the difference. On the term that was multiplied by the exponential, I get the step function plus a shifted version of my inverse. Instead of t, it's t minus 4 pi. On the other one that wasn't multiplied by the exponential, it's just the cosine. I just invert it normally, as I normally would. We were thinking that we would have a solution that involved oscillations from the start because our spring mass had some initial position. And we have that. We have oscillations from the get-go in this cosine term. But then we were also thinking that something in the solution should kick in at time 4 pi. And we have that as well. We have this step function and these sine oscillations kicking in at time 4 pi. So this is doing what I would expect it to do, and this is the solution to a delta function forcing term differential equation with Laplace transforms.